Hello everybody, this is Dr. Christopher White, and now we're moving on to the second half of lecture number 9, during which we're going to be looking at marine depositional environments. Alright, so these are the environments that we've looked at so far. We've looked at the continental environment, so we've looked at fluvial systems, desert systems and glacial systems. And we also looked at the transitional environment, so deltas, beaches, barrier islands and tidal flats. So now we are moving on to the marine environments. So essentially these are depositional environments that are constantly submerged underwater. So marine environments can include environments located on the continental shelf. So that's the area of seafloor just off the coast that has a water depth between 0 and 200 meters. Then we have the continental slope. So essentially that's the slope that comes after the continental shelf. It's often quite steep. At the bottom of that we have the continental rise, and then from then on we have the deep sea floor, which is also referred to as the abyssal plain. So the vast majority of eroded material from the continents ends up in the marine environment. So most of the stuff that's eroded from the land will be transported by rivers and deposited into the oceans. Now, we not only have clastic sediments in these systems, we also have chemical sediments and sediments that are formed by organic processes. So we have limestones and evaporites that can also form in these environments. In the case of both limestones and evaporites, they're both shallow marine environments, and so they're going to be forming on the continental shelf. Okay, so this is the diagram we've seen already. So this is just highlighting the marine environment. So we're looking at essentially the continental shelf, the continental slope, which includes submarine fan environments, the deep marine environments, and organic reefs. So this diagram here kind of shows you it in slightly greater detail. So here's the continental shelf. So that's 0 to 200 meters water depth. Then as we go across the edge of the continental shelf, which is referred to as the shelf break or the slope break, we then go down the continental slope. And the continental slope is often quite steep, typically 45 degrees or steeper, going all the way up to near vertical. Now the continental slope is cut by numerous canyons, and along these canyons you will have essentially mass flow, so underwater landslides, and these produce turbidity currents. Now we've already touched on turbidity currents. We discussed them as part of the not previous lecture, but part of lecture 8. So as material comes down, it comes down the continental slope, and of course it comes to a stop as it begins to move onto the flatter terrain of the continental rise. So the continental rise consists of material that's fallen off the continental shelf, come down the continental slope, and come to a stop at the bottom. Now once we head off the continental rise, we head into the abyssal plain, and that's essentially the deep sea environment, and that's going to be very, very flat and relatively low energy. So essentially we transition from the high energy continental shelf environments into the essentially sporadically high energy continental slope and continental rise environments into the very low energy abyssal plain environments. Okay, so let's think of the detrital marine environments first. So the first marine environment into which detrital sediments will be deposited is the continental shelf. So that's between 0 and 200 meters water depth. So it's a gently sloping region which is adjacent to the continents, and it's typically underlain by continental crust. So the shelf environment consists of a high energy inner portion, so that's the part that's closest to the continent, and that's typically dominated by sands, and they are often, the sands are often disturbed by waves and tidal currents. The inner portion of the shelf sediment, as I said, is mostly sand, and you will mostly see very large-scale crossbeds. So there's lots of dunes, underwater dunes, within this environment closest to the coast. Now, once again, just like beach deposits, although these crossbeds, can be on a meter scale, so they could look like desert sands, in reality, we are going to look for things like pieces of shell, and that's going to tell us that we're in a marine environment. Also, like beach sands, typically the sands you get will very often, or should I say dune sands, will very often be not as well sorted as desert sands, not as well rounded, and they'll often have a higher proportion of feldspar in them. So bedding planes are commonly marked by waveform ripple marks. That's another indicator that we're in a marine environment that's constantly being churned up by wave action. So these waveform ripple marks are another indicator that we're really not in a desert environment. So we'll often obviously have lots of marine fossils and lots of biotubation. There'll be lots and lots of burrows. Now, as we move away from this, essentially this inner portion of the continental shelf, we'll move out into a lower energy environment that tends to be dominated by muds. So this transition between the higher energy sand environment and the slightly lower energy mud dominated environment can either be a sharp transition or it can be a gradational transition. So once again, if you think back to our previous lecture about sedimentary facies, you will know that essentially the contact can essentially be a sharp contact or it can grade. If it's a sharp contact, it will often intertongue. So over time, the contact will often move backwards and forwards, producing a zigzag pattern. Now, you're asking the question of, well, why is it sandy closest to the coast and slightly muddier slightly further out? And it's relatively straightforward. So closest to the coast, we have lots of it's relatively high energy, lots of waves, tidal forces. So what these tend to do is they tend to pull very small sedimentary particles like clays and silts away from the area closest to the coast and out into deeper water. And so the clays and the silts that are in this inner portion get pulled out into deeper water, and they'll be deposited when the water becomes a bit more low energy and a bit more stable. And so essentially that's why you have very little silt and clay closest to the coast, and it gets more mud rich as you head out of this sandy zone. Okay, so that's why it goes from sand to muds. Now, it's not written on here, but as we head even further out, once the clay and silt has left the water, well, that means the water that's towards the edge of the continental shelf. So we have the sandy portion here, closest to the coast. We have the muddy portion slightly further out. Now, by this point, there's most of the clay and silt has left the water. So by the time you're out here on the edge, the water quality is often quite good. The water is very, very clear. Now, if you have the right conditions, this is the area where you will start forming coral reefs and therefore limestones. So in a classic model, it goes from sandy facies to mud facies to carbonate facies. Now, as I say, conditions have to be right to get carbonate facies, and we're going to discuss carbonates in a couple of slides' time. So then we come to the slope and the rise. So once we're at the edge of the continental shelf, we hit the shelf break, which is this line coming along here. Now, the sudden drop off, essentially, this is the edge of the continental crust. So it's oceanic crust over here, continental crust here. So the continental shelf and the continental slope is continental crust. The continental rise and the abyssal plain is oceanic crust. And essentially, this slope here represents the edge of the continental crust. So most of the sediment that enters the marine environment crosses the continental shelf and eventually makes it to the shelf slope break. Now, obviously, once it goes across the shelf slope break, it will then come down the continental slope and it will come to rest, so it'll come to a stop on the continental rise. So as I've already said, the sediment is funneled down the continental slope along submarine canyons. So the sediment moves down the continental slope as turbidity currents, these underwater landslides, which we discussed in Lecture 8. So the sediment ends up forming a sequence of overlapping submarine fans. And if you remember, these submarine fans have this distinctive 5-layer boomer sequence, and that tells us they've been formed by turbidity currents. So the continental rise down here is essentially produced by the build-up of material by one turbidity current and another and another and another. So you have lots of these fans overlapping on each other to produce the continental rise. So the continental rise is pretty much nothing but turbidite sediments which present this boomer sequence. So submarine fans will either present normal grading, that's turbidite, so coarsest at the bottom, finest at the top, or in some cases they may present inverse graded bedding, that's finest at the bottom, coarsest at the top. Now, inverse graded bedding shows that we don't actually have a turbidity current, we simply have a debris flow. Now, that really is an underwater landslide. Okay, so it's slightly different from a turbidity current. Now, depending on what type of material is falling down the continental slope, the size of the fans produced will vary. So if we look at this diagram over here on the left, we can see different fan sizes, and we can look at what's changing. So down here we have a relatively small fan, only about 10 kilometers. Now that's potentially when we have sand-rich fans. So sandy material is quite heavy. So as the turbidity current comes down the slope, hits the continental rise, as it starts to lose energy, it will very quickly deposit this sandy material, and so you're going to have relatively small fans. Now compare that to a mud-rich fan. Now a mud-rich fan, on the other hand, it's going to come down the continental slope, so the turbidity current comes down the continental slope, and as it hits the continental rise, it starts to lose velocity, but because the material being transported is so light, so it's only clays and silts, that flow will continue for much, much longer. And so you end up with very, very large submarine fans. And you can kind of see that here. So here's a good example here on the east and west coast of India. We have the Indus fan on the west coast and the Bengal fan on the east coast. And you can see the size of these fans. And that's because the rivers producing them are transporting huge quantities of muddy sediment from the Himalayas, and so they've got very, very mud-rich fans which extend a very, very long distance into the Indian Ocean. You know, compare that to fans, for instance, like the fan associated with the St. Lawrence River coming off Canada. Well, that fan is, the St. Lawrence River transports a lot of very sandy material produced by the erosion of granites in Canada. So that means you get lots and lots of sand, and so the fans that are produced are considerably smaller. So when we look at this diagram here, what's it actually showing us? Well, we have the continental shelf in pink, the continental slope in green, the continental rise in yellow, and the major fans in red. And you can see that in a lot of cases, the fans don't really extend past the continental rise because the continental rise is mostly made up of this fan material. Only in the case of the largest rivers, so like the Ganges, the Amazon, the Mississippi, does the fan extend beyond the continental rise. So what's actually going to cause these turbidity currents? What's going to make them happen? Well, turbidity currents can be caused by one of three things. The first one is earthquakes. So simply an earthquake occurs, it shakes the continental shelf, any loose sediment here, essentially at the shelf slope break, will become loose and it will slide down the continental slope, producing a turbidity current. Not really that difficult to understand. The next one is slope collapse. Now that's due to do with the steepness of the slope. So if you've ever built a pile of sand at the beach, for instance, you will know that as you pile more and more sand on, the steepness of the slope on your hill gets higher and higher and higher, doesn't it? It gets steeper over time. And you'll know that there comes a point where sand starts to roll down the side of the hill. That's called the angle of repose. There's an angle at which your material becomes naturally unstable, and it will begin to slide. So on a loose material like a clastic sediment, once you reach the angle of repose, the material will naturally start to slide. So if you get a build-up of material over here at the shelf break, well, over time as you pile up more and more material, the steepness of that pile gets higher and higher and higher. Eventually you'll hit the angle of repose, the material becomes unstable, and it just slides. And of course that material then starts sliding down the continental slope, once again producing a turbidity current. The final thing that can trigger a turbidity current are strong storms. So let's think of Hurricane Harvey. So Hurricane Harvey hit Texas and it really churned up the water, just off the coast of Texas. Okay, really churned it up. So, most of the time it's only the inner portion, the sandy portion of the continental shelf, that really gets churned up by wave action and tidal action. However, every once in a while when there's a very, very strong storm, that will start to churn up the deeper portions of the continental shelf, and that can push material towards the edge, and then finally down the continental slope. So turbidity currents can be caused by earthquakes, slope collapse, or strong storms. So next we have the deep sea and abyssal plain environments. So the deep sea floor is covered by fine-grained deposits known as pelagic sediments or pelagic clays. So the exception to this are the mid-ocean ridges that occur at the center of the ocean basins, and that's where new crust is being created. And as new crust is being made there, well, that new crust hasn't had time to be covered by any kind of sediment. So mid-ocean ridges tend to be relatively sediment-free. If you ignore those, on the other hand, the abyssal plain is essentially relatively flat, and it's covered by very clay-rich sediments. So these sediments that we see are pretty much sand and gravel free. And that's simply because the environment is so low energy, the water does not have the capacity to transport those class sizes. Now, we've also mentioned, though, there are some points on the Earth's surface where you will have sand and gravel sized material, maybe cobble sized material, being deposited by icebergs. And it's a process called ice rafting. And you will typically find the deep marine environment closest to Greenland, and Antarctica will very often show coarser sediments because of all the material that's being deposited from melting icebergs. But in most cases, the ocean, the abyssal plain will be pretty much dominated by nothing but clay. So pelagic sediments are split into three groups: siliceous oozes, calcareous oozes, and red clays, also called pelagic clays. So what's an ooze? So an ooze consists of equal to or greater than 30% calcareous or siliceous planktonic debris. So what are we talking about? Well, it just so happens that the little photosynthesizing plankton, the algae that float on the top of the oceans, some of them have shells. And those shells can be made of calcium carbonate, or they can be made of silica. And so when that organism dies, well, obviously the organic portion is going to decompose. However, the shell will slowly sink and will eventually make it to the seafloor. And obviously it will be incorporated into the seafloor sediments. So in areas where we have sufficient calcareous or siliceous shelled planktonic organisms to deposit enough material, their shells will become incorporated into the deep sea sediments in sufficient quantities to achieve a level of greater than or equal to 30% of the total sediment, in which case it will be classified as an ooze. If you have less than 30% of the total sediment made up of planktonic debris, these planktonic shells, then it will simply be classified as a red clay or a pelagic clay. So obviously carbonaceous oozes, calcareous oozes, contain calcareous shells, so calcium carbonate shells, and siliceous oozes contain siliceous shells, so silica shells. I don't know why I put carbonaceous there, that should read calcareous, my apologies for that. So the remainder of the sediment will obviously be clay. Now the accumulation rates of these sediments are extremely low. So calcareous oozes accumulate at between 0.3 and 5 centimeters every 1,000 years, and siliceous oozes accumulate at 0.2 to 1 centimeter every 1,000 years. Now the rate of accumulation compared to red clays is quite high. And the reason for that is you're getting lots of material that's being contributed by the dying plankton. And that makes the rate of sedimentation a little bit higher for calcareous and siliceous oozes. Now, calcareous shelled microorganisms are more common than siliceous shelled microorganisms, so you tend to get a higher rate of calcareous ooze deposition. And silica-based or silica-shelled organisms tend to be more common in colder waters, so siliceous oozes tend to be associated with higher latitudes towards the poles. Now, red clays, also called pelagic clays, accumulate in the deepest portions of the oceans, and their rate of accumulation is between 0.1 and 0.5 centimeters every 1,000 years. It's extremely slow. So these pelagic clays will contain less than well, essentially less than 30%, organic material, or should I really say, shells. So the material that makes up these pelagic clays consists of wind-blown sands. So if you remember, when we were talking about the deserts, we were talking about how the wind is capable of transporting the very, very fine silt and clay-sized particles long distances. And we refer to that as loess. Well, some of that will end up in the oceans. And so it will slowly sink to the seafloor, where it will become incorporated into deep sea sediments. They can be clay minerals contributed by rivers. So as the river enters the ocean, some clay-rich water will slowly make its way way out to sea, and those clay minerals will fall onto the deep sea floor. It can be volcanic ash from very, very large volcanic eruptions. There can, of course, be microfossils, so essentially the shells of calcareous and siliceous organisms. They can be iron oxides contributed by submarine vents, otherwise known as black smokers. And then there can be a few other bits and bobs, including meteorite dust coming from space that can be incorporated into the sediment. So these pelagic clays consist of a real mixture of different materials. However, the rate at which those materials enter the deep marine environment is relatively slow, and so the rate of sedimentation is also very, very slow. So the red colour for these pelagic clays comes from a coating of iron and manganese oxide minerals. It's primarily the mineral limonite or limonite, depending on how you want to pronounce it. Now what happens is when the sediments that contain limonite get lithified, so during the process of taking the sediment and turning it into a rock, the limonite will break down and it will form hematite, which gives the rock a very distinct, strong red colour. So pelagic clays will tend to form in areas where planktonic activity is low. If it was high, you would obviously have lots of plankton dying, and so their shells would become part of these deep sea sediments, and so you would end up with a calcareous or siliceous ooze. And so obviously pelagic clays can only form in areas where the amount of plankton is much lower. So as we've already discussed, the presence of particles larger than silt is due to iceberg-related dropstones or meteorites every once in a while. And this diagram here shows you the distribution of pelagic clays. So what you'll notice is we have the pelagic clays, so the red clays themselves. They are in this red colour, and you can see most of the time they tend to occur in these very deep ocean basins well away from the continents. Okay. In terms of the calcareous oozes, the light purple, you can see they cover, once again, a very, very large portion of the ocean. Now, in terms of the siliceous oozes, so that's made of radiolarians and diatoms, those are two different types of organism that use silica to make their shells. What you'll notice is, in the case of these siliceous diatoms, they are located in very, very high latitude environments close to the poles. That's because they like cold water. In the case of the radiolarian oozes, you can see they're located in the middle Pacific over here, and their population is primarily controlled by the circulation of water in the South Pacific. Essentially, it's moving from South America, coming across to Southeast Asia, where it gets warmed up and then comes back towards South America again. Okay, so that current is sometimes referred to as the El Nino if it gets particularly strong. Okay, so next we have carbonate environments. Now, I think it's time to take a quick break. So pause the presentation, get up, have a walk around, go in a glass of water, and come back in a couple of minutes. Okay, so next are the carbonate environments. So carbonate rocks are typically dominated by one of two minerals. One mineral is calcite, and one mineral is dolomite. So carbonate rocks that are dominated by calcite are simply referred to as limestones. In the case of dolomite, if dolomite dominates the rock is often referred to as a dolostone. Now, in the vast majority of cases, most carbonate rocks are limestones. However, during the lithification process, so the process of taking that calcium carbonate rich sediment and turning it into a rock, what happens is in some cases the calcium carbonate sediment comes in contact with a fluid that contains magnesium. And when that happens, the calcium carbonate reacts with that magnesium-bearing water typically, and it produces dolomite. So during the process of diagenesis, it's very common for limestones to be turned into dollostones. So limestones are similar to detrital rocks in some ways, as they often contain varying proportions of sand to gravel-sized allochems. So we've left the detrital rocks now, we're into the carbonates. So the term clastic no longer applies. So what we have now are particles that are essentially sand and gravel sized, but they are no longer called clasts. They are now referred to as allochems. And there'll be things like, ooids and bits of shell, so shell fragments. So there is normally also a component of micrite. So micrite is often referred to as lime mud. It's very, very fine-grained calcium carbonate that has, that essentially, if you were to touch it, you would think it was mud. However, unlike detrital sediments, the particles that make up limestones are formed in or near the environment of deposition. So there's typically minimal transport involved. As they form in marine environments, there will be some degree of sediment reworking. So it's not uncommon to find in limestones that formed in relatively shallow water, you can typically find crossbeds, ripple marks, and maybe even mud cracks if you have micrite that's being exposed to the air. Although limestones can form in lake environments, the vast majority of limestones form in warm, shallow, clear seas that are between 30 degrees north or south of the equator. So carbonate shelves are typically located in continental shelf environments with water depths between 0 and 200 meters. There's also another thing called a carbonate platform, and that occurs in regions of high topography, usually seamounts or isolated reefs. Okay, so there's two different carbonate producing environments. We're going to cover the carbonate shelves and the carbonate platforms. So deposition occurs in environments where there is little detrital sediment, especially mud, because clear water is important. You need nice clear water if you're going to start forming reefs, and reefs help to protect the environments that form limestones. So, if you think of it, an environment like the Caribbean, for instance, what you have are lots and lots of islands that have relatively short, small rivers, and those small rivers do not put much water do not put much sediment into the Caribbean Sea. So the water quality there is very, very good. In contrast, think of the area around Texas. Well, obviously, the Buffalo Bayou puts in huge quantities of very muddy water into the sea, and so that inhibits the formation of reefs, for instance, and so therefore it reduces the possibility of forming limestones. Now, carbonate shelves are the dominant location for carbonate deposition because you can form huge quantities of limestones in these environments. So the shelves will often feature a raised area referred to as a carbonate barrier just before the shelf begins to drop away into deeper water. So typically when you look at the location of these carbonate barriers, they are most commonly found right before the shelf break. So they're in essentially right at the edge of the continental shelf, just before you go over down the continental slope. Most carbonate barriers form in moderate to high energy environments, and they're typically reefs. Okay, reefs like to be in relatively energetic environments because the constant water movement means there's a good supply of food. Some barriers can be made of skeletal particles, so fossils, shells, bits of shell, or they can be made of a buildup of ooids, but the vast majority of carbonate barriers are reefs. So carbonate barriers tend to be structureless. They just tend to be a mass of carbonate material. And as I said, they can be composed of corals, mollusks, or sponges. So most carbonate barriers are reefs. And a reef literally just builds up by bits of dead coral falling over and new corals growing on the top of them. So over the time you just build up a mound essentially of coral material, with new coral constantly growing on the top of the old dead coral. So these carbonate barriers essentially protect a carbonate lagoon behind them. So the reef itself will be essentially just a mixture of, a randomly piled up mixture of fossils, typically pieces of, sorry, I'm not saying, I should stop saying fossils. I should say coral material, so fragments of old dead coral, whilst the carbonate lagoon behind will be a protected environment. So within the lagoon, we often get things called carbonate banks, and those are essentially are linear bodies of carbonate that form within the lagoon, and they are made up of horizontal beds. We can often find in the lagoon, we can also get cross beds and ripple marks. And when we find there's micrite that's been exposed, we can sometimes get mud cracks. Now, in most carbonate lagoons, the most common type of carbonate material we get is micrite. So lagoon sediments are often micrite dominated, but you will obviously get abundant marine fossils and bioturbation. So these carbonate lagoons are very, very rich in, for instance, mollusk fossils, and they're very, very rich in, worms burrowing through this, carbonate mud, this micrite. So, don't think that carbonate lagoons are just going to be nothing but micrite. There's typically a lot of life within these carbonate lagoons as well. Now, the question you're probably wondering is, well, how does micrite form? So, micrite is means microcrystalline calcite. So, how do you actually get it? Well, there's one of a couple of ways you can form micrite. The first way is, due to organisms that eat shells. So there are some types of algae that will eat shells, and they will look for organic material stuck between the layers in a shell. So think of an oyster shell. If you've ever picked up an oyster shell, you'll know that on the outside it has a layered appearance. And so each time a layer of calcium carbonate was added to the shell to make it bigger, some organic material will get stuck between those layers. And so there are some organisms that will eat through the calcium carbonate of the shell, looking for the organic material that has gotten stuck between those layers. Now obviously they're looking for the organic material to eat, but they can't eat the calcium carbonate. And so what do they do with the calcium carbonate? They simply essentially get rid of it as a waste extract. They poop it out. And so the first way you can form micrite is simply by, as part of the the inedible portion of essentially a shell that one of these burrowing organisms is moving through. Now, the other way you can form micrite is if you get the precipitation of very small calcium carbonate crystals onto the bodies of photosynthesizing algae which live in the lagoon. So the lagoon is a lovely protected environment, and it's typically in a nice warm area of the globe, because you require typically warm, clear water. And so very often these lagoons are absolutely stuffed with photosynthesizing algae. And so what happens is calcium carbonate crystals will precipitate out of the water onto the bodies of these algae, and eventually the algae die, and the calcium carbonate crystals that are on their body will be essentially fall off the decomposing body, and they will become incorporated into the sediment that makes up the lagoon. Okay, so micrite can either form through burrowing microorganisms that are eating shells, or they can form from the precipitation of calcium carbonate crystals directly onto algae within the lagoon. And obviously when the organism dies, it releases those calcium carbonate crystals that become incorporated into the lagoon sediments. So just to give you some idea of what a carbonate lagoon looks like, here's a nice example. This is the Florida Keys. And so you can see here, this is the carbonate barrier. So this is actually an old reef. So once upon a time, this area was underwater, but since this area formed, there has been a sea level drop, and the reef became exposed. And so obviously, we've now built on top of it. Now behind it, we have the protected carbonate lagoon. And within the carbonate lagoon, we have these carbonate banks, these linear bodies, and they essentially link together these patch reefs, these little essentially circular reefs that form within the carbonate lagoon. Now you'll notice that the lagoon has a very kind of white colour to it, and that's because of the large amount of micrite that's within the water and within the sediments of the lagoon. It gives it this very distinct white colour. Now what's happened is as the sea level has dropped, a new reef has actually formed slightly further out. So this here is actually the shelf break. Okay, this is the edge of the continental shelf, and we actually have a new reef forming along here. You can kind of just about make it out there. And so there's actually a new carbonate lagoon forming behind this new reef. So this is the kind of classic carbonate shelf system. We have a barrier at the front protecting a carbonate lagoon behind, where in some cases huge quantities of carbonate can be deposited. So this is another example over here. This is northeastern Australia. So this is the Great Barrier Reef area. So over here we have the Pacific, over here we have Australia. Now what you'll notice when you look at this area of Australia around here is it's a relatively dry area. So there are very few rivers depositing sediment into the sea here. So that means this water is going to be pretty clear. It's also in an area that's, relatively warm. So you have nice, warm, clear, shallow water. The perfect conditions for reef formation. So you can see along the shelf break here, we have a line of reefs forming. And behind the reefs, we have a carbonate lagoon. Now we can see within the carbonate lagoon, we have several patch reefs. And over time, these patch reefs will get linked together by carbonate banks, and those carbonate banks will essentially produce individual isolated pockets within the carbonate lagoon. So as you can see, the size of this area here is massive. And so eventually, once the carbonate barrier, once the reefs become large enough and they protect this area sufficiently, you will end up forming an absolutely massive carbonate lagoon capable of producing huge quantities of limestone. Now compare that to the Florida Keys. The Florida Keys in reality will only produce a relatively small quantity of limestone. This area here, northeastern Australia, if things go to plan, will produce a massive quantity of limestone. So that's how you can produce huge expanses of limestone. So there's the barrier reef, here's the carbonate lagoon, these are the patch reefs within the lagoon, and this is the continental slope dropping down towards the abyssal plain over here. And that's the continental slope itself. So in contrast to the carbonate shelves, the carbonate platform environment exists because there is a topographic high big enough to produce an area of shallow water. So the most common topographic high is a seamount. Seamounts are typically extinct volcanoes on the seafloor. And obviously, like any volcano, they tend to be quite tall, and the upper portions of the volcano can sometimes end up producing a water depth of around 0 to 200 meters. So as long as this topographic high is essentially produces an area of ocean, seafloor that's between 0 and 200 meters, and it's in an area that has nice warm clear water that's typically between 30 degrees north and south of the equator, you have the possibility of forming reefs. So these platforms will often develop a carbonate reef on the windward side of the platform, and that reef will protect a carbonate lagoon behind. And so here's an example that's found just off the northern coast of Venezuela, and you can see, so here's the reef coming around here, protecting the carbonate lagoon directly behind. Now, I'm not sure what is actually causing this topographic high, but I would postulate it's probably a seamount, an extinct volcano. And so what we have is, here's the reef, so that's building up on the windward side of the platform, and so behind it we have the carbonate lagoon that's being protected by the reef, and in here we have carbonate deposition. You can see that once again because it has this very distinct creamy white colour. So this diagram here kind of shows you, the basic idea. So on the windward side we have the reef forming, and that's going to protect the carbonate lagoon behind. And so within the carbonate lagoon, typically we'll get the formation of carbonate muds directly behind the reefs. That's micrite. And then further back, we'll tend to get the slightly larger carbonate particles. So we might get ooids forming, and we might get a buildup of very shell-rich material back here, and that will eventually be turned into fossils if the sediment becomes liquefied. So those are our two different environments. So carbonate shelves will produce a very large carbonate lagoon that can sometimes produce very, very large quantities of limestone. In contrast, the carbonate platforms will often only produce relatively small quantities of limestone because they're not that big in their, in their lateral extent. So now let's think about evaporites. So evaporites obviously occur when you have water evaporating away. So common minerals that occur in evaporite deposits are the halides. So that includes any mineral that contains chlorine, typically, so chlorine or fluorine. So that includes minerals like halite, otherwise known as salt, or sylvite, which tastes like salt but is slightly bitter compared to regular salt. And then we have the sulfates. So that includes minerals like gypsum, so that's calcium sulfate, which contains water in the case of gypsum, or anhydrite, that's calcium sulfate without water. So typically in environments that are very, very hot, you will preferentially form anhydrite over gypsum. However, if the evaporite is forming in an environment where it's a bit more, a bit wetter, you will tend to form gypsum over anhydrite. So small evaporite deposits are associated with playa lakes and saline lakes. So, playa lakes we've already discussed. Those are lakes that form in desert environments, and saline lakes, that's an environment like the Dead Sea. It's a very large lake, but essentially it's in a desert environment, so the water is slowly evaporating away. Saline lakes can also be associated with lagoons, associated with barrier islands. However, if you want to really form substantial quantities of evaporite minerals, the only real way to do it is to essentially isolate a large portion of the ocean. So evaporites are far less common than detrital or carbonate sedimentary rocks due to the very limited controls on their formation, and the fact that once you form an evaporite mineral, if you then put seawater back on top of it, that seawater will then start to dissolve the evaporite mineral. So it's very easy to essentially dissolve any evaporite minerals that are formed and dissolve them back into seawater, and they will be lost. Okay, so we've been going for 40 minutes now. So once again, time to take a quick break. So pause the presentation, get up, have a walk around, get a glass of water, and come back in 2 or 3 minutes. Okay, so now let's keep going with evaporites. So locally, evaporites can be very, very important. So large evaporite deposits occur in Western Canada, Ohio, New York State, Northern Europe, and in several Gulf Coast countries. And they're actually quite important because evaporites form what we tend to refer to as a seal for oil and gas. So oil and gas typically can't move through layers of evaporites. So oil will typically be formed in a mudstone. The oil itself will then leave the mudstone. It will then typically go into what we refer to as a reservoir rock, very normally a sandstone. And the oil will want to naturally rise. However, if there's something that stops it rising, like a layer of evaporites, which seals the layer, then essentially the oil gets stuck in what we refer to as a trap. The oil can't get out. And so then we come along several million years later, pump the oil out of the ground, and make ourselves a fortune. So in terms of evaporites, the best example of a layer of evaporites is the fact that there is a layer under the Mediterranean seafloor that's 2 kilometers thick. So once upon a time, I'm just trying to think of when it was, let's say about 20 million years ago, the Mediterranean Sea became isolated from the Atlantic Ocean. So if you think of the modern Mediterranean Sea, it's only connected to the Atlantic Ocean through the Strait of Gibraltar that separates Spain from Morocco. So imagine if something blocked that strait, then essentially the Mediterranean Sea would no longer be communicating with the Atlantic Ocean. It would no longer be able to exchange water. Well, at that point, the only sources of water coming into the Mediterranean would be rivers like the Nile or the Danube. And the Mediterranean is a very, very hot area, so the water would be evaporating very, very quickly, and so it's unlikely that the Nile and the Danube and the other rivers could contribute sufficient water to keep the Mediterranean at its current level. So the Mediterranean would begin to evaporate away, and eventually it would lead to the deposition of evaporite minerals. And that's exactly what happened approximately 20 million years ago. The Mediterranean became isolated, and it resulted in the deposition of a layer of evaporites that were approximately 2 kilometers thick. So that's quite a substantial layer. So the exact conditions of formation for an evaporite are actually disputed. When we're talking, with the real fine details, that are required. Now, on the whole, though, we are very, very certain about the broad details that are required to form evaporite minerals. First of all, you need an arid region. Within that arid region, you need a restricted basin. So you need a body of water that's trapped in an area. It can't get out. And you need rates of evaporation that are in excess of the rate of replenishment. You need to be losing more water than is being put into your basin. And so that will lead to a net loss. And over time, you will essentially begin to increase the salinity of the water within your basin, and eventually you'll reach a point where you'll start to deposit evaporite minerals. And these conditions are best met in coastal regions and arid areas. For instance, the Persian Gulf is a really good location for looking for modern day evaporite deposits. So as we've already touched on, if the water within a lagoon can become isolated enough from the ocean, well, in that case it will form a restricted basin, and if rates of evaporation are high enough, then the water within the lagoon will slowly begin to evaporate away, and the lagoon will slowly become more and more saline. And a good example of that is St. Lucia Lake in South Africa. And St. Lucia Lake is on the east coast of Africa, so this is the Indian Ocean over here. And the lagoon itself is connected to the ocean by an inlet which is down here. It's off the bottom of the picture, you can't see it, but it's not a very big inlet. So as we can see, the lagoon is isolated from the Indian Ocean, and it's in a very hot area, relatively arid, and so the water in Lake St. Lucia is evaporating away, and it's leaving behind the evaporite minerals. So you can see Lake St. Lucia has this kind of white creamy appearance because of the evaporite minerals that are essentially in the water. And so Lake St. Lucia is a lot like the Dead Sea. The Dead Sea sits between Israel and Jordan. And once again, that's another lake. The Dead Sea is only fed by the River Jordan from the north, and the amount of water being contributed by the River Jordan into the Dead Sea is lower than the amount of water being lost to evaporation. So essentially there's a net loss, and so slowly but surely the Dead Sea is becoming more and more salty, more and more saline. So now we need to think about how we actually interpret depositional environments. So geologists must always take care when interpreting using the available data. So let's look at this conglomerate. We can see a picture right here. So if we don't collect the right evidence, it's impossible to tell if this conglomerate was deposited by a braided river or a glacier, or maybe this conglomerate represents some kind of beach deposit in a very, very energetic beach environment. So what would we look for? Well, first we would look at the grain size. Specifically, is there any mud present? Well, mud is only deposited in very, very low energy environments. So if there's mud present, that gives us some idea about how energetic the system was. So then if we can, we would look at the geometry of the layer. What does it look like in 3 dimensions? Does it produce one of these shoestring bodies like a piece of spaghetti? Does it produce a sheet-like morphology like a thin, very laterally extensive layer? Or does it produce a lenticular body, the kind of thing we might get, for instance, in a point bar in a meander? So we would look for around for any other evidence. For instance, are there any glacially polished rocks nearby? Do those rocks have striations? That would tell us maybe this sediment could be, related to glacial processes. And then we'd also look to see, well, are there any marine fossils present? Well, if we can find marine fossils in this conglomerate, well, that would instantly make us think, well, it's highly unlikely to have been deposited by a glacier. It would also be highly unlikely to have been deposited by a braided river. So that would instantly mean that if we find marine fossils, we'd think, well, this conglomerate could have been formed on a very energetic beach that's being hit by very, very big waves, powerful waves. So then we would also say, are there any indications of uni or bidirectional flow? Well, if we can find some kind of indication of unidirectional flow, that means whatever was moving the sediment was only moving in one direction. So that would instantly make us think river. On the other hand, if there were indications of bidirectional flow, well, that would suggest that we were looking at waves. So obviously the wave goes up the beach, then it comes back down the beach. There's a flow in 2 directions. And as we discussed in lecture 8, that's going to produce 2 distinct types of dunes and 2 distinct types of ripples. So unidirectional flow will produce an asymmetrical ripple. Bidirectional flow will produce essentially a symmetrical ripple. So based on the previous picture, it looks like there's relatively little mud present and there's no obvious structure. So it's probably a braided stream deposit. So let's just go back to it. So, we can't really see much mud. It looks to be mostly sands and gravels, maybe even verging on a cobble. Okay, so the system has to be quite energetic. Now, the lack of mud suggests that obviously, we're not dealing with a glacial system. So we're not dealing with a till. So glacial tills contain everything from clay-sized particles all the way up to, cobbles and maybe even boulders. So the fact there's very little mud there means we can pretty safely discount glacial till as the likely source for this sediment. Now that leaves us with, maybe braided river systems or possibly, very energetic beaches. So, when it comes down to it, it's a bit difficult to tell the difference. There's no obvious indication there's any kind of fossil shelly material in this layer, so that would suggest it's probably not a beach deposit. And so that means by the process of elimination, we're left with braided river. So all you have to do is collect the right evidence and then put that evidence together to form a coherent argument. Essentially, being a geologist is a bit like being a detective. Essentially, as long as you collect the evidence and you can put it into a coherent argument, you can work out what happened. So let's look at another example. So this is the Navajo Sandstone in the southwestern United States. So the Navajo Sandstone is a well-sorted sandstone. The clasts within the sandstone are well-rounded, and it's a very quartz-rich sand with clasts typically between 0.2 and 0.5 millimeters. That's a very tight size range. Within the Navajo Sandstone itself, we can find tracks of land animals, so we clearly know that we are on the continents. This sediment must have formed essentially in a continental setting. We can also see crossbeds that are up to 30 meters in height. We can also see there are some ripples as well. Now, 30 meters in height is probably a bit too big for most rivers. So that makes it difficult for us to think that this sand was probably deposited by a river. There's also the fact that, we obviously wouldn't get the tracks of land animals if this was a river deposit. Okay, and the other thing is that if this was a river deposit, we would typically see a shoestring morphology. It would look like a piece of spaghetti in 3 dimensions. However, what we see when we look at the Navajo Sandstone is it has a blanket morphology. So you have layers that are very, very laterally extensive. That's the kind of thing you would expect to see in a desert setting. So the most logical explanation is that the Navajo Sandstone formed in a desert. And when we look at the crossbeds, we can see, we can look at the direction in which they're dipping, at which they're angled, and we can see that they are dipping towards the southwest. Therefore, we know the prevailing wind was coming from the northeast and going in a southwesterly direction. So once again, that tells us something about what was happening in the past. So we know, once we date the Navajo Sandstone, let's say the Navajo Sandstone, for argument's sake, formed in the Triassic. Therefore, we know in the Triassic, in the area that we're looking at, we know that it was a desert, and we know the prevailing wind direction was from the northeast going southwest. So that's quite a lot of information we've managed to gather just by looking at one outcrop. So if we look at lots of outcrops, we can produce what's referred to as a paleogeographic map. So essentially that deals with the geography in the Earth's past. So what we have to do is we have to go to numerous outcrops and we have to look at rocks that are the same age. And so what we'll do is we'll go to lots and lots of outcrops and we'll look at all the different rocks and we'll look at the depositional environment at the same time. So we'll look at rocks, let's say, that formed at the end of the Cretaceous, and we'll look at the depositional environments at the end of the Cretaceous across lots and lots of different outcrops. And so some of those outcrops will have formed, in continental systems, some of those outcrops will show transitional systems, and some of those outcrops will show marine systems. And so by looking at those outcrops, we can say, right, this outcrop was underwater, this outcrop was on the continent, this outcrop, represented the transitional environment like a beach. And so that means we can work out the paleogeography, what areas were above sea level, what areas were below sea level, and what areas were along the coast. So that allows us to essentially gauge on some local scale. It allows us to gauge the climate, the prevailing wind direction, possibly the amount of rainfall, the types of rivers we have, the power of those rivers, the organisms that are present. And all this evidence gets put together to form a paleogeographic map. So paleogeographic maps can essentially be done on a local scale, a regional scale, a continental scale, or if you have enough information, a global scale. So here's an example from the textbook. So this example covers the central and southwestern United States in the Cretaceous. So what's happened is in these states, geologists have gone to lots and lots of outcrops, essentially dating to the Cretaceous, and they've looked at the type of rocks that are there. Are they marine rocks? Are they transitional rocks? Are they continental rocks? And so they've come up with the environmental deposition for each outcrop, and they've essentially put all the outcrops together to work out, areas that essentially represent the continents, areas represent the marine environments, and also then they've also put them into, subgroups. Is this a, alluvial fan environment? Is this a desert environment? Is this a lagoon environment, for instance? And so this is the type of map they've come up with. And so over here we have two greens. So we have land, moderate to low elevation, sediment source. And in light green here we have land, high to moderate elevation, sediment source. So that's a mountainous terrain. So we know that in the Cretaceous, this green band here represents mountains, or at least very big hills. And that's where material's being eroded to produce sediment that's going to be transported. And that sediment's going to be transported out of the mountainous terrain by rivers. And in some cases, those rivers are going to be short-lived and they're going to produce alluvial fans. So if you remember, alluvial fans form along the margin of mountainous terrain. So these alluvial fans are in exactly the right location along the edge of this band of mountainous land. So as we move past the alluvial fans, we move into this light brown band. And this light brown band represents, where is it? Here we go, non-marine rocks, coastal plain, primarily sandstone. So what we're dealing with here are rocks that are not marine, so we can discount, any kind of marine rocks. And they are continental, and they're coastal plain, and they're primarily sandstones. So what we're probably dealing with is an area that essentially is near the coast. So as sea level rises and falls, the coastline moves backwards and forwards a little bit, and we have lots and lots of sand in this area, and the sand is going to be moved around by the wind. So we're going to have a desert environment that essentially has a beach environment as well. So most of this is going to be desert, and this portion along here closest to the water is going to be a beach depositional environment. Now within this desert environment we have a isolated body of water, which is this green area here, and those are coal swamps. So that's going to be a lake. So, and that lake is going to be full of organic material, full of plants, and those plants are going to die, they're going to fall over, their material is going to be incorporated into the lake sediments, and that they went to form layers of coal later on. And so what we have here is, a mountainous terrain feeding sediment onto this desert plain. In this desert plain we have one lake, and we know the coastline is going to be along here because this dark brown rock are marine sandstones, barrier islands, and beaches or nearshore deposits. So essentially this is essentially a transitional environment grading into a marine environment. Essentially this represents the inner portion of the continental shelf. Then we're moving out into deeper water, moving out into the pink environment. Those are marine shales. So now we've gone from sand facies into mud facies. And then we're going to continue out even further into these into this darker brown color here. These are marine calcareous mudstones. So now we're moving out into carbonate facies. So we have the classic continental shelf environment: sand facies, mud facies, carbonate facies. And so essentially we know that from this evidence during the Cretaceous, this area of the southwestern United States represents essentially the margin of a shallow, warm sea. So, and all we have to do is just gather evidence from lots and lots of locations and gather evidence from all the rocks that date to the Cretaceous. So it's a relatively simple method that gives us very, very powerful, important results. And so, that tells us something about, the geology, but it's also quite useful. So, for instance, if I was looking for, something like a lithium deposit, if I was looking to mine lithium, well, in that case, I would know instantly that lithium tends to be associated with lakes that, formed in relatively dry areas, these player lake deposits. And so I might be tempted to kind of look in this area here. And so I think, well, there's a good chance, I might be able to find some kind of lithium deposit that I could mine in these Cretaceous age rocks associated with this lake. And so, this information is not only helpful from a scientific point of view, it can also be helpful from an economic point of view. So here's another example from the textbook. So this area, once again, we're still in the southwestern United States. We've gone for a slightly smaller area now. And so what we've done is we're looking at rocks that are of, I will find the date somewhere on here. These rocks are of, where are we? Eocene age. So they're from the Cenozoic. So not that long ago. And so once again, what we're looking at is we have rocks that are of a continental setting. So we see things like alluvial fans, we see floodplains, we see swamps. So clearly, we're on the continents. In terms of the rocks we see, well, we see the brown rock, these brown areas, and these kind of, light browny areas. They represent areas of high relief and moderate relief. So those are the source areas for sediments. That's where the sediment is coming from. So we have high ground all around here, and that's supplying sediments that are clearly being distributed across these green areas here that represent floodplains. So we clearly have rivers coming off the high ground, and those rivers are actually transporting the sediments produced by the erosion across the floodplains. Along the margins of these areas of topography, we have these alluvial fan deposits. Okay, and we are obviously, as you come off the alluvial fan deposits, we have these floodplains that are covered by large rivers that are transporting the sediments coming off the mountains. Now, in some areas we have swamps, so we have coal deposits. So that tells us we have an area of very subdued topography that's partially flooded. So once again, think any of swamp environment. Think the swamps of Louisiana, for instance, that kind of environment. Now, then we also can see, as we look in these areas here, we have lake sediments. Okay, these are going to be mostly mudstones consisting of very, very finely laminated layers. And so just by, once again, tying together all these rocks that are Eocene in age, we can come up with an idea of what the depositional environment was like during the Eocene. So once again, once I do this and I have an idea of what the environment was like, well, if I'm interested in coal, I would instantly focus in on this area up here, because I know from my analysis that this area was once upon a time a swamp. And so that made me think, well, there's a good chance this area may contain coal, in which case that would be the best place to drill to see if I could find some. So okay, so we've made our way through these different depositional environments. So we've done the continental environments, the transitional environments, and the marine environments. So let's just take a second to do the code word for this presentation. The code word for this presentation is going to be Shakespeare, as in William Shakespeare. So that's the code word, and I believe that's it for the presentation. All right, good work. Take care. I will see you guys soon.